Hey, what's up? It's your old pal, Mr. Cook, and we are making our way through the Unit 5 probability group work. So I just went through the first 3 problems. Now we're going to go through the permutations, combinations problems before making our way to the word problems, the more rigorous word problems with data tables and things like that. So the first one is a problem that is specifically made for one solving method. This is how many distinguishable arrangements can be made with the letters of calculator. So since there's a lot of letters that repeat in here, like the C's, for example, if I were to switch these 2 C's around, technically that's moving the letters around, right? But does it make a new word? It shouldn't, just because the C's are changed, it's still the word calculator. So like this presents a problem. There's these repeated values in here that kind of mess up the arrangement of the letters. I mean, like if you just mixed up, these 10 letters, that would be an easy answer, right? Like, if they were distinguishable letters, just unique letters, it would just be 10 factorial because this should be a simple permutation, to work through. But since we have these repeats here, we need to kind of divide those parts of it out. So what we do is we just divide out, the repeated values as they're listed. So like we go through letter by letter, each unique letter, and divide out the repeats. So for C's, for example, I've got 2 of those. So I divide out 2 factorial for the C's. Then I go to each individual letter. So the A's, I've got 2 of those. So I divide out another 2 factorial. L, I got 2 of those L's. So I divide out another 2 factorial. And then the rest of them are all just singletons. So the U, the T, the O, and the R. So I mean, you can add those in, but it's redundant to do so. So like 1 factorial for the U, 1 factorial for the T, 1 factorial for the O, and 1 factorial for the R. But obviously these are just 1, so it doesn't affect anything. Anyways, we just type this into our calculator. You can even do some of it kind of, on your own. 10 factorial divided by, and then 2 factorial is just 2, so 2 times 2 times 2 is 8. And then, you just type that in at that point, So we've got 10 factorial, so 10, and then math, probability, factorial, and then divided by 8. And you get your answer, 453,600 different arrangements, of the letters. Okay, so there's your answer for that one, 453,600. And these ones have like a bunch of really interesting like applications. I wish we had more time in class because we could go over some really neat ones. And actually, like, this is one of those forgotten things that the kids can use in the AMC, to help out a lot. Like one of those little tools that helps out a lot is the distinguishable values. But anyways, we'll cross that bridge a little bit later. Maybe I'll put together a video at some point on just studying for the AMC with, stuff from this class. Anyways, let's move on to the next part of it. So number 5, let's read through it. It's a committee comprised of, all right, so I'm just going to stop there. Whenever you see a keyword like committee or group or something, like 99 times out of 100, it's going to be a combination rather than a permutation. Let's see why that's the case. So this says a committee comprised of 3 math majors and 4 science majors. Why do they have more science majors than math majors? That doesn't, I don't know, maybe I'm biased, but yeah, they should have more math majors in there. Is to be selected from a group of 20 math majors and 16 science majors. Look, they even have more math majors. They should have more representation in the committee. How many different committees can be formed? Well, this committee is really comprised of 2 different committees, right? One for math majors, one for science majors. So using the counting principle, we need to multiply these together because they're different events. Picking a committee for math majors, picking a committee for science majors. Now, when we're talking about a committee, it's really just a group of people. And that's what a combination finds. It's a group of elements that are indistinguishable from another. Like if I get a group of, math major A, maybe one guy's name is like Bill, and then another one's name is Heather, and then another one's name is Frank, and another one's name is like Donna or something, like 4 people. Oh yeah, it's supposed to be 3 math majors. So these are the science majors. And then if I rearrange that group, does it make a different group? No, of course not. Like, it's just a group of people. When the groups are indistinguishable, even if you switch them around, that's a combination because it's just simply gathering together a group. So this group that we're making for the math majors is comprised of, like, we're taking from 20 different math majors and we're getting a group of 3. So it's 20 combination 3 because that's the group size. This is the number of people that we're taking from that group. I'm sorry. 3 is the group size. 20 is the original people that we're picking the group from. Then we have 16 science majors, so that's 16 combination 4. And then we're set to go because we've got our little math group and our little science group, and then we multiply them together to make the entire group. So just, let your calculator do the rest of that stuff, obviously. Let's see what we got here. So 20, and then math, probability, NCR, and then 3, all right, and then times 16 combination 4. Then we get a bunch of different ways to make these groups. Looks like 2,074,800 different groups that we can make from this, different committees that we can make. Cool, so that's our answer for that one, 2,074,800 committees. How many ways can the top 3 places of a race be selected from a total of 30 competitors? I'm probably going to change the wording of this for future classes because I don't really like this part of it. This is top 3 places. I like it better when it says specifically that they're in first, second, and third place because that's like distinguishable. Whereas like if you say top 3 places, that could also imply that you're just looking for the number of people that placed in the race. That's a thing, like where it doesn't matter if you got first, second, or third, like you placed in the race, so you got top 3. And I don't want it confused between those two. I want to make sure that like you guys understand like the difference between having established roles or placements or rankings versus just having like a group of people. For the context of like, seeing this on a test, we'll have like specific roles in a group that tell you that it's a permutation versus just saying like, leaving it ambiguous and assuming that you might have a group instead. Because that's the difference between the two. A permutation is always going to be like individual roles, individual rankings, individual positions or placements. Like when the order matters, that's a permutation. That's what it means. So if you wanted to look for specific placing, first, second, third, that would be 30 different competitors, and then you have 3 different positions or rankings that you have. So 30P3. And that number is, let's see what that is. With our calculator, 4,060. So that's the number of different ways that you can get first, second, and third with these 30 competitors. That's different from, just seeing who placed, that way it doesn't matter if like Sarah and Lenny and Carl, if they got first, second, and third, right? Like if we're talking about just how they placed, it wouldn't matter if like Sarah was in third, Carl was in first. So that means it would be a combination. So like we say that when it says placed, that's a combination. So like 30 combination 3, and then that'd be a different number altogether. So 30C3. Oh wait, I did 30C3 already. Dang it. Sorry about that. I didn't put permutation. So yeah, made a mistake. I'll go back on that. You probably already saw that, didn't you? Of course you did. All right, so let me rewrite that in here. So 30 permutation 3. Yeah, so that's like a way bigger number. I should have seen that was a small number. Shame on you, Mr. Cook. So 24,360. There we go. That's the real number. And notice that like this is like a way bigger number than this one. It's because each individual ranking makes a different one. So, it's different from just like the group. Okay, so that's the next 3 problems. That's permutations, combinations. Now I'm going to start up the word problems, and those ones will go a lot faster.